space around our home galaxy is far emptier than it should be. We live in a cosmic neighborhood called the local group, a collection of dozens of galaxies dominated by our Milky Way and the great spiral of Andromeda. According to our most trusted theories of the universe, the vast halos of dark matter surrounding these giants should be teeming with hundreds of smaller dwarf satellite galaxies. Yet our telescopes reveal only a scattered handful. This glaring discrepancy is known as the missing satellites problem, and it is one of the most significant cracks in our understanding of the cosmos. By the end of this exploration, you will understand the 25 deepest mysteries behind this cosmic vanishing act, from ghostly dark matter halos to explosive stellar feedback. We will investigate why entire galaxies seem to have disappeared from plain sight, and what their absence reveals about the fundamental laws of the universe. Are these missing satellites hidden in plain darkness, or did they never form at all? Our cosmic census reveals a shocking shortfall. The very first and deepest mystery of the local group is the simple, staggering deficit of dwarf galaxies. This is the heart of the missing satellites problem. To understand why it's so puzzling, we need to look at the universe's blueprint, the Lambda CDM model. This is our standard model of cosmology, and it has been incredibly successful at explaining the large-scale structure of the cosmos. It tells us the universe is made of ordinary matter, and dark energy. According to this model, dark matter is cold, meaning its particles move slowly, and it clumps together gravitationally from the very beginning. Supercomputer simulations that follow this recipe, like the landmark Millennium simulation, paint a very specific picture of how galaxies like ours should form. They show vast halos of dark matter collapsing, with smaller clumps or subhalos falling into orbit around the larger ones. These dark matter subhalos are the seeds for satellite galaxies. The simulations are clear. A galaxy the size of the Milky Way should be surrounded by not dozens, but hundreds of these dark matter clumps massive enough to pull in gas and ignite stars. We should be living in a crowded metropolis of small galaxies. Yet when we look up, our sky tells a different story. Astronomers have confirmed only about 60 satellite galaxies around the Milky Way. That's not just a slight miscalculation, it's an order of magnitude difference. Where are the other several hundred? This discrepancy isn't unique to our home. Our great galactic neighbor, the Andromeda galaxy, shows a similar pattern. While Andromeda has more known satellites than we do, the count still falls far short of the theoretical swarm. This tells us the missing satellites problem isn't a fluke of the Milky Way. It's a universal feature. It's a fundamental challenge written into the fabric of our local group. If our best model of how the universe works predicts a sky filled with hundreds of faint, dancing dwarfs, and we see only a quiet handful, then something in that model is incomplete. Either the dark matter behaves differently than we think, or something happened to those galaxies that our simulations have missed. The quiet emptiness around us is the first loud clue that our cosmic story has missing pages. The silence of our galactic neighborhood holds a second, stranger mystery. Even the dwarf galaxies we can see are not behaving as they should. This is known as the too big to fail problem. It is a related but distinct puzzle that deepens the enigma. Think of it this way: if the missing satellites problem is about a missing crowd, the too big to fail problem is about the few people who did show up, but arrived in tattered clothes when they should be wearing fine suits. Our most sophisticated simulations predict that the largest dark matter halos captured by a galaxy like the Milky Way should be massive enough to act as powerful gravitational anchors. They are too big to fail at the task of galaxy formation. Their gravity wells should be deep enough to easily pull in and hold onto vast clouds of gas, the fuel for new stars. These halos should have given birth to bustling, bright dwarf galaxies, some perhaps even rivaling the small Magellanic Cloud in splendor, yet that is not what we find. Instead, we observe satellites like the Fornax and Sculptor dwarf galaxies. They orbit the Milky Way and sit in dark matter halos that, according to theory, are among the most massive of their kind. They should be brilliant, but they are faint, ancient, and gas-poor. Fornax and Sculptor are essentially fossils, dominated by old stars with very little ongoing star formation. They are cosmic ghost towns built on foundations meant for metropolises. So what happened? What process could have so efficiently quenched star formation in such massive and seemingly robust systems? It suggests a force even more powerful than their own considerable gravity was at work, something that either stripped away their gas fuel or prevented them from ever using it fully. This forces us to question the very environment of the early local group. Was it a more violent and hostile place than our simulations portray? The too big to fail problem tells us that the mystery is not just about galaxies that are absent, but also about galaxies that are present yet strangely, profoundly dim. Their quiet light is a signal of a forgotten conflict. The faintest whispers of starlight are now telling their own story. Among the handful of satellites we have found, a new class of galaxy emerged only in the last 2 decades, the ultra-faint dwarfs. These are not just dim galaxies, they are the ghosts of galaxies. Objects like Segway 1 and Boötes 1 are so tenuous they contain only a few hundred ancient stars, lost in the vast darkness of their own halos. Finding them was like spotting a single candle on a distant mountain in the dead of night. Their discovery is our third mystery, and it adds a crucial piece to the puzzle. These ultra-faint dwarfs may be the closest thing we have to a direct fossil from the universe's infancy. They are so small and primitive that they likely formed their stars in one brief, early burst and then stopped, freezing in time. This leads directly to our fourth mystery, the shadow of reionization. To understand this, we must go back over 13 billion years. After the Big Bang, the universe cooled into a fog of neutral hydrogen gas. Then, the first stars and galaxies ignited. These pioneers did not just bring light, they brought a cosmic firestorm. Their intense ultraviolet radiation began to blast through the cosmic fog, heating the gas and stripping electrons from hydrogen atoms in a process called reionization. This epoch of reionization was a fundamental transition for the cosmos, but for the smallest dwarf galaxy seeds, it may have been a death sentence. The theory is starkly elegant. The smallest dark matter halos, the ones that should have grown into many of our missing satellites, were also the most vulnerable. Their gravity was too weak to hold onto their gas against the onslaught of this pervasive ultraviolet background. The gas was heated and evaporated away, or blown out by the pressure of the radiation itself, before it could ever collapse to form many stars. In this scenario, reionization did not destroy galaxies, it sterilized them. It left behind dark matter halos that are almost entirely empty, or populated by just a few hundred stars that formed in a narrow window before the cosmic lights switched on. These, then, could be the missing satellites, not truly missing but hiding in plain sight as the ultra-faint dwarfs. So, does this solve the problem? It provides a compelling and likely vital chapter. Reionization can explain why the smallest predicted satellites are so incredibly faint, but many astrophysicists argue it is not the complete answer. The epoch of reionization was a global event, yet the missing satellites problem is particularly acute right here in the local group. Could the same process also explain the too big to fail galaxies, those massive halos that should have been resilient to such radiation? The debate continues, suggesting that while reionization cast a long shadow, another, more local force may have also shaped our quiet galactic neighborhood. The nature of dark matter itself is now under scrutiny. Our fifth mystery confronts a key prediction about how this invisible substance should behave. According to the cold dark matter model, dark matter particles do not interact with light or with each other, they only feel gravity. In a galaxy, they should sink to the center, piling up into an extremely dense, sharp peak called a cusp. Think of it like a steep, narrow mountain at the very heart of every dark matter halo, dwarf or giant. This cusp should create a very specific gravitational signature, one that astronomers can test by watching how stars orbit within a dwarf galaxy. Their speeds should increase sharply as they approach the dense central cusp, yet when observations of certain dwarf spheroidal galaxies, like Fornax, are analyzed, the story changes. The orbital speeds of stars suggest something different, a gentler, flatter central distribution of mass. Instead of a sharp mountain peak, the data often points to a soft, rounded hill, a core. This discrepancy between the predicted cusp and the observed core is a direct challenge. It implies that dark matter might not be completely cold and collisionless after all. Perhaps some unknown interaction, some tiny force between dark matter particles, is at work, preventing them from clumping so densely. Or perhaps something dramatic happened inside these galaxies to reshape their dark hearts. This leads us directly to our sixth mystery, a powerful and violent candidate for that reshaping, supernova feedback. Early in a dwarf galaxy's life, it would have experienced frantic bursts of star formation. Massive stars live fast and die young, exploding as supernova in brilliant, catastrophic detonations. One supernova is a tremendous release of energy, but imagine dozens or hundreds going off in quick succession within the fragile confines of a small galaxy. This isn't just fireworks, it's a sustained cosmic hurricane. The combined force of these explosions can blow the galaxy's gas clean out into intergalactic space. But the effect may go even deeper. As vast plumes of gas are violently ejected, the gravitational landscape of the entire galaxy changes in a flash. The sudden loss of mass causes the gravitational potential, the shape of the galaxy's gravity well, to slosh and fluctuate wildly. This chaotic motion can act like a giant mixer, dynamically heating the dark matter itself. The dark matter particles get stirred up, their orbits becoming more random and spread out. Over time, this relentless churning could transform a dense central cusp into a smooth, fluffy core. It is a breathtaking idea that the death throes of stars could sculpt the invisible skeleton of a galaxy. This process could solve two puzzles at once. It provides a plausible mechanism to create the observed dark matter cores, and it also explains why many dwarf galaxies are so faint and gas-poor today. The supernova literally blew their future fuel away, quenching star formation and leaving behind a quiescent, ancient stellar population orbiting within a reshaped dark matter halo. But the critical question remains, is this stellar feedback powerful enough? Can the energy from dying stars truly overcome the immense gravitational grip of a dark matter halo, especially in the more massive, too-big-to-fail systems. Some simulations suggest yes, while others indicate it may only work for the smallest dwarfs. The search for answers is pushing our simulations to new levels of detail, modeling not just dark matter, but every stellar explosion and gust of galactic wind. The orderly arrangement of our galactic companions presents a seventh mystery that defies our expectations of cosmic chaos. Look at the brightest satellites of the Milky Way, the large and small Magellanic Clouds, the Sagittarius Dwarf, and others like Draco and Ursa Minor. For decades, we assumed they orbited our galaxy in a random, swarming cloud, like bees around a hive. But detailed mapping has revealed a pattern so precise it sends chills down an astronomer's spine. These major satellites are not scattered randomly at all. Instead, they are aligned along a vast, incredibly thin plane, a great disk of dwarfs that slices through the Milky Way. This structure is not just a slight clustering, it is a pronounced and rotating disk, with most of these galaxies moving in the same direction along this shared celestial highway. The probability of such a neat, rotating alignment happening by pure chance in the standard model of galaxy formation is astronomically small, akin to tossing a handful of marbles into the air and having them land in a perfect, spinning circle. The standard model predicts satellites should fall into the Milky Way's grasp from all directions, tracing messy, independent orbits that create a roughly spherical cloud. This discovery of a coherent plane forces us to question that fundamental picture, and our local group neighbor deepens the intrigue, as a similar, vast plane of satellites has been identified orbiting the great Andromeda galaxy. Two dominant galaxies, each with its own improbably arranged entourage. Coincidence seems an increasingly frail explanation. So what could create such startling cosmic architecture? One compelling theory looks to the distant past, to a time when the Milky Way was not just pulling in dark matter clumps, but vast rivers of primordial gas. If satellites formed within a great, rotating disk of this infalling gas billions of years ago, they might have inherited its orderly motion, preserving that fossilized plane to the present day. Another idea suggests group infall, where several dwarf galaxies fell into the Milky Way's grasp together as a pre-existing swarm, their shared initial trajectory locking them into a common plane. But the most radical theories look beyond gas and groups, questioning the fabric of the cosmos itself. Could the existence of these planes hint that dark matter interacts in ways we do not yet understand, or that gravity behaves differently on galactic scales? The Great Disk of Dwarfs is a silent, spinning monument in our sky, a structure so clear and yet so unexpected that it points to chapters of galactic history we are only beginning to read. Far from the gravitational grasp of giants, another mystery quietly unfolds. Our eighth mystery lies in the deep fields between the great spirals, focusing on the quenched, isolated dwarfs. If the too-big-to-fail problem is about satellites being strangely quiet, this puzzle is about loners who have fallen silent for no apparent reason. Standard logic tells us a dwarf galaxy floating in the emptiness of intergalactic space should be a haven for star formation. It holds onto its precious gas clouds, free from the violent tides and stripping winds of a massive neighbor like the Milky Way. With a steady fuel supply, it should be a bustling stellar nursery, glowing with the light of young blue stars. Yet our telescopes reveal a population of isolated dwarfs that are just as quenched, just as red and ancient as those orbiting giants. They have mysteriously shut down. Take the enigmatic dwarf galaxy known as Leo T, discovered in 2006. It lies over 1 million light-years from the Milky Way, a true isolate in the void. Leo T presents a fascinating contradiction. It contains a population of very old stars, evidence of star formation that occurred billions of years ago. But it also holds onto a small, cool reservoir of neutral hydrogen gas. This gas is the raw material for new stars, yet for reasons we do not fully understand, Leo T is not using it. It is like finding a car with a full tank of gas, a working engine, and no driver, simply parked and silent for eons. So what happened? What internal clock or external influence could cause a galaxy all by itself to simply stop creating stars? One possibility points back to the long shadow of reionization. Perhaps the cosmic ultraviolet background, that pervasive afterglow from the first stars, was enough to heat the gas in these small, isolated halos just enough to prevent it from cooling and collapsing efficiently. The process would be achingly slow, a gradual stifling over billions of years rather than a violent expulsion. Another idea looks inward, to mechanisms of self-quenching. Could a single, intense burst of early star formation have produced enough supernova to blow out the galaxy's own gas, leaving behind just a wispy remnant like we see in Leo T? In such a small system, even a modest burst of stellar feedback might have catastrophic and permanent consequences, dooming the galaxy to an early retirement. The existence of these quenched isolates tells us that the story of galaxy evolution is not solely written by dramatic encounters and cosmic collisions. Sometimes the silence is born from within or from the faint, diffuse glow of a universe still echoing with its first light. Their quiet presence in the lonely voids forces us to consider more subtle, patient forces at work across cosmic time. The chemical fingerprints of ancient stars hold a ninth, profound mystery. To understand it, we must think of a galaxy not as a single object, but as a cosmic archive, its stars like pages in a history book written in the language of elements. Every star carries within it the chemical signature of the gas cloud from which it was born. When astronomers read these signatures in the oldest stars of the Milky Way's halo, the vast, sparse cloud of stars surrounding our galaxy's main disk, they find something unexpected. These halo stars are rich in what are called alpha elements, like oxygen, magnesium, and silicon. These elements are forged primarily in the violent, short-lived deaths of massive stars as supernova. Their abundance tells a story of rapid, early enrichment. Now, compare that to the chemical book of a typical surviving dwarf satellite galaxy, like Sculptor or Fornax. Their ancient stars show a different pattern, with lower ratios of these alpha elements to iron. This distinct signature suggests a slower, more extended chemical evolution, one paced by a different type of supernova. This is the puzzle. If the Milky Way's halo was built, as we believe, from the shreds of countless smaller galaxies that merged with us over billions of years, then the chemical makeup of those building blocks should match the stars in our halo today. It is a simple case of cosmic inheritance, but the surviving dwarf satellites, the very objects we think of as the leftover building blocks, do not match. Their chemical books are written in a different dialect, so where are the true progenitors, the gas-rich, chemically matching galaxies that actually donated their stars to build our halo? They appear to be missing. One possibility is grimly final. Perhaps those true building block galaxies were indeed completely destroyed in the merger process, torn apart so thoroughly that not even a recognizable core remains, their stars scattered seamlessly into our halo. Their unique chemical signature was simply diluted and lost in the vast stellar sea. Another, more tantalizing idea is that they are not gone, but transformed. Could these progenitor galaxies be hiding among the faintest population we have already discovered, the ultra-faint dwarfs? Each of these ghostly systems could be the dense, surviving core of a much larger galaxy that was stripped bare. If we could take a detailed chemical census of their few hundred stars, we might find that some ultra-faints carry that critical, alpha-rich signature that matches the Milky Way's halo. They would be the surviving shrunken hearts of the giants that built our home. This chemical mismatch is a quiet but devastating clue. It tells us that the dwarf galaxies we see orbiting us today may not be the pristine building blocks of our past, but a biased sample of survivors. The real architects of the Milky Way may have sacrificed themselves completely in the construction, leaving behind only their scattered stars and this enduring chemical mystery. The very motion of our galaxy holds a clue to the darkness around us. Our 10th mystery is a cosmic timing test, one that pits the movement of giants against the quiet of the void. It begins with a simple observation. The Andromeda galaxy is not standing still relative to the Milky Way. It is on a direct course toward us, destined for a colossal collision billions of years from now. But this approach is not a simple fall. By measuring its subtle sideways motion, astronomers see that Andromeda also has a small, tangential velocity, meaning our two galaxies are not just falling directly together. They are also slowly swinging around each other like partners in a slow, grand dance. This orbital dance is the key to the timing argument. The logic is elegant. If you assume the Milky Way and Andromeda have been moving under their mutual gravity since the universe began, you can use their current separation and approach speed to calculate the total mass that must be pulling on them. It is a cosmic scale, weighing the entire local group by watching how its two biggest members move. The result is startling. The timing argument suggests the combined mass of the Milky Way and Andromeda is far greater than the sum of their visible stars, gas, and even their own estimated dark matter halos. It points to a vast reservoir of additional mass, a heavy cloak of darkness enveloping our entire neighborhood. So where is this extra mass? One compelling answer connects directly to our core mystery. This missing mass on the grand scale could be the collective gravity of hundreds of unseen dark matter halos, the very predicted satellites that are missing in light. Each of those dark subhalos, even if it failed to form stars, still contributes its gravitational pull. Like invisible dancers in the ballroom, their combined presence would tug on the Milky Way and Andromeda, influencing their orbital waltz in a measurable way. The timing argument, then, may not be revealing missing mass in a vague sense, but specifically the mass of the missing satellites themselves. It is a breathtaking idea that the solution to one dynamical puzzle could be the hidden cause of another. The silence in our telescopes could be echoing in the very motion of the galaxies we see. This transforms the missing satellites problem from a local galactic issue into a defining feature of the local group's entire gravitational architecture. The emptiness is not empty at all. It is filled with the unseen anchors of dark matter, their silent weight guiding the future collision of giants. Deep within the faintest stellar halos, a different kind of absence is felt. Our 11th mystery is not about missing galaxies, but about a missing class of cosmic object that should, by all rights, be hiding within them, the intermediate mass black hole. These are the crucial missing link in the black hole family tree. We know of stellar mass black holes, born from collapsing stars, and we know the behemoths, the supermassive black holes that anchor galaxies like our own Milky Way. But what lies in between? Theory strongly suggests there should be black holes with masses ranging from a few hundred to a few 100,000 times that of our Sun. These intermediate mass black holes are the hypothesized seeds from which the supermassive giants grew, especially in the early universe. And where is the most logical place to find such a pristine, ancient seed? Within the oldest, smallest, and most chemically simple systems we know, the ultra-faint dwarf galaxies. These dwarfs, with their handful of ancient stars, are perfect cosmic time capsules, largely untouched by the violent mergers that scrambled larger galaxies. If an intermediate mass black hole was planted there in the infancy of the universe, it should still be there, a silent, heavy heart at the galaxy's core. Finding one would be a monumental discovery, a direct window into how the first supermassive black holes were born. Yet, despite dedicated searches, the evidence remains frustratingly elusive. Astronomers look for two key signatures. First, they measure the velocities of stars near a dwarf center. An intermediate mass black hole's immense gravity would make those stars whip around at noticeably higher speeds, creating a detectable spike in motion. Second, they search for specific X-ray or radio emissions, faint glows that might occur if the black hole is slowly accreting or feeding on wisps of nearby gas. While there have been a few tantalizing candidates, like in the dwarf galaxy called Leo I, conclusive proof has remained out of reach. The searches have largely come up empty. This presents a stark puzzle. Are intermediate mass black holes truly absent from these dwarfs? If so, it challenges a major pathway for how supermassive black holes form, forcing us to consider that they might have grown from entirely different, perhaps more exotic, seeds. Or is the problem with our vision? Could these black holes be so quiet, so starved of material in the gas-poor ultra-faints, that they emit virtually no detectable radiation? And could their gravitational influence be so subtle, spread over such a small cluster of stars, that our current telescopes simply cannot measure the telltale stellar motions with enough precision? The absence of evidence is a profound clue in itself. It tells us that the early universe may have been a place where building a black hole was a much more complex and difficult process than we imagined, or that these ancient seeds are masters of cosmic hide and seek, waiting for the next generation of observatories to finally reveal their shadowy presence. This statistical shortfall has its own precise name, the satellite luminosity function. It is our 12th mystery, and it frames the entire problem in the cold, clear language of mathematics. Think of it not as a list of missing objects, but as a cosmic census report gone wrong. Astronomers create this function by plotting a graph. On one axis, you have the brightness or luminosity of a satellite galaxy. On the other axis, you have the number of satellites that are that bright. Our most sophisticated simulations of cosmic structure produce a very specific prediction for this graph. It shows a steeply rising curve. As you move to the left toward fainter and fainter galaxies, the predicted number should skyrocket. The universe, in theory, should be absolutely teeming with incredibly dim dwarfs, each sitting in its own dark matter halo. This is the statistical heartbeat of the cold, dark matter model. Now, we plot the actual data from our local group. The line we draw is profoundly different. For the brighter dwarf galaxies, like the Magellanic Clouds, the observed count and the predicted count are not too far apart. But as we slide down the brightness scale into the realm of the ultra-faint dwarfs, the two lines violently diverge. The observed line climbs only a little, then seems to flatten out or even drop, while the predicted line soars upward into the hundreds. The gap between these two lines is the missing satellite's problem, quantified. It is a vast, empty space on the graph where points should be, but are not. This raises two critical and very different possibilities. The first is a problem of human limitation. Could it be that these ultra-faint dwarfs exist in the predicted numbers, but are simply too dark and diffuse for our current telescopes to see? Finding a galaxy like Segway 1, with only a few hundred stars spread across thousands of light years, is like searching for a wisp of smoke against a black velvet sky. Our census is almost certainly incomplete. This is where monumental surveys like the Dark Energy Survey and the upcoming Legacy Survey of Space and Time come in. These projects are not looking at a single patch of sky. They are systematically mapping enormous swaths of the universe, using the most powerful digital cameras ever built to detect the faintest possible smudges of light. They are our best hope for completing the census, for filling in the faint end of that graph with real data points. Every new ultra-faint dwarf discovered is a precious data point. But the second possibility is more fundamental and unsettling. What if the graph is telling us a deeper truth? What if there is a physical cutoff, a minimum mass or density threshold below which a dark matter halo, no matter how pristine, simply cannot ignite and sustain star formation? Perhaps the smallest halos were so vulnerable that the epoch of reionization sterilized them completely, leaving behind absolutely dark halos with zero stars. In that case, the luminosity function would have a natural floor, and the faint end of the observed graph would never rise to meet the theoretical prediction, because those objects are not galaxies at all. They are just lumps of dark matter. The race is on between these two ideas. With every new sweep of the sky by these immense surveys, we edge closer to an answer. Will they discover a rising tide of ultra-faints that finally makes the observed graph match the prediction, solving the mystery through sheer numbers? Or will they find that the curve truly does flatten, revealing a fundamental limit to galaxy formation and forcing us to rewrite the rules for the smallest dark matter halos in the cosmos? The violent tides of our galaxy may have already consumed its missing satellites. This 13th mystery confronts a brutal and elegant solution: tidal disruption. Picture the Milky Way not as a gentle host, but as a cosmic force with immense gravitational reach. As a smaller dwarf galaxy ventures too close on its elliptical orbit, it does not simply fly by. The side of the dwarf facing our galaxy feels a stronger gravitational pull than the side facing away. This difference in force, the tidal force, stretches the satellite like taffy. Over countless orbits, this relentless pulling and squeezing strips away the dwarf's outermost stars and gas, which are most loosely bound. These stolen stars are flung into long, arching ribbons that gradually mix into the Milky Way's halo, becoming what we call stellar streams. The most spectacular example is the Sagittarius Stream, a great river of stars wrapping around our sky, the dissolving remains of the Sagittarius dwarf spheroidal galaxy. This process is real, and we are watching it happen. The logical extension is stark. Perhaps hundreds of predicted satellites suffered this fate long ago. They were not missing, they were dismantled. Their stars were digested into our halo, and all that remains today are their dark matter halos, now empty and starless, orbiting the Milky Way as ghostly shadows. These are the ghost halos, the invisible corpses of galaxies. This idea beautifully accounts for the missing light, transferring the stars from many small galaxies into the diffuse glow of our own stellar halo. But could destruction on this scale truly be the complete answer? Astronomers debate the math intensely. Simulations show that while tidal stripping is effective, it may not be efficient enough to have destroyed hundreds of substantial satellites within the age of the universe. The process takes time, and many dwarfs on wider, slower orbits might have survived. Furthermore, tidal disruption leaves behind evidence, the stellar streams themselves. If hundreds of dwarfs were torn apart, our halo should be crisscrossed with dozens of distinct, bright streams, a tangled web of galactic debris, yet we see only a handful of major streams like Sagittarius. Where are all the others? This absence of streams is a powerful counter-argument. It suggests that either the destruction rate was lower, or the galaxies being destroyed were so faint and star-poor to begin with that their stellar streams are impossibly dim, mere whispers lost in the background starlight of the halo. This brings us back to the earlier idea of reionization. If most of the smallest dark matter halos never formed many stars, then their tidal destruction would leave no stellar stream at all, only an invisible ghost halo. The silence in the stellar stream census may itself be a clue, pointing toward a population of satellites that were born dark, lived dark, and died dark, leaving nothing for our telescopes to see but the echo of their gravity. But what if the dark matter itself is not what we think? Our 14th mystery confronts a radical alternative, the possibility of warm dark matter. This idea challenges the very foundation of our standard model. For decades, the cold dark matter paradigm has reigned supreme. It assumes dark matter particles are heavy and slow-moving, cold, allowing them to clump together easily from the smallest scales upward, seeding those hundreds of dwarf halos. Warm dark matter proposes a fundamentally different particle, one that is much lighter and faster. These particles would have zipped through the early universe at significant speeds, a property with a dramatic consequence. They would have washed out small-scale fluctuations. Think of it like trying to build a sandcastle in gently flowing water. The finer details, the tiny turrets and walls, get smoothed away before they can set. Only the larger mounds, the bigger structures remain. In cosmic terms, warm dark matter suppresses the formation of the smallest dark matter halos right from the beginning. There would be no hundreds of tiny seeds orbiting the Milky Way, because the universe never made them in the first place. This elegantly cuts the knot of the missing satellites problem by stating the predicted swarms were never there to be found. The observed handful of bright dwarfs would then correspond to the rare, larger halos that managed to form in this smoother landscape. It is a compellingly simple solution. Yet, as with all profound ideas, it comes with serious trade-offs. The same suppression that removes excess small halos could also make it harder to form the very first galaxies in the early universe. If warm dark matter is too warm, it might delay cosmic dawn, contradicting what we already observe about the timing of the first stars. So how do we test this? Astronomers use a cosmic barometer called the Lyman alpha forest. When light from distant quasars travels through the universe, it passes through clouds of neutral hydrogen gas. These clouds absorb specific wavelengths, creating a forest of dark lines in the quasar's spectrum. The distribution of these clouds, especially the smallest, densest clumps, is exquisitely sensitive to the nature of dark matter. Cold dark matter predicts a thick, fine-grained forest full of tiny absorbers. Warm dark matter predicts a sparser forest, with the smallest clumps erased. Current data from instruments like the Keck Observatory and the Very Large Telescope tightly constrain how warm the dark matter can be. It cannot be so warm that it completely eliminates all small-scale structure, because we do see some. Furthermore, the mere existence of the ultra-faint dwarf galaxies themselves places a lower limit on the particle's mass. If dark matter is too light and fast, even the halos hosting these faintest dwarfs could not have formed. The fact that we have found objects as tiny as Segway one tells us that whatever dark matter is, it must be cool enough to allow for structures on that scale. So, while warm dark matter remains a fascinating and viable alternative, it cannot be a panacea. It must walk a narrow line, suppressing just enough small halos to explain the missing satellites, while still allowing for the earliest galaxies and the faintest dwarfs we observe. This delicate balancing act makes it one of the most intensely scrutinized ideas in modern cosmology, a reminder that the solution to our local mystery may lie in the fundamental identity of the universe's most abundant, yet most elusive, substance. The intricate dance between starlight and dark matter may be choreographed by the explosive deaths of stars themselves. This 15th mystery plunges us into the complex world of baryonic physics, the physics of ordinary matter, and its power to reshape the cosmos. While dark matter provides the gravitational stage, it is the ordinary stuff of stars and gas that writes the visible script. Modern supercomputer simulations have evolved far beyond tracing only dark matter. They now attempt to model the full, messy reality of galaxy formation in what are called hydrodynamic simulations, like the FIRE and Illustris TNG projects. These are not just gravity calculations, they are virtual universes where gas can cool, condense into stars, and where those stars live out their lives and die in spectacular supernova explosions. The goal is breathtakingly ambitious: to see if the detailed physics of ordinary matter can solve the multiple satellite puzzles at once. Can supernova feedback, modeled with exquisite detail, successfully suppress star formation in the smallest halos? The simulations suggest a powerful yes. In these virtual worlds, when a dwarf galaxy begins to form its first stars, the ensuing supernovae do not just blow bubbles, they drive colossal galactic winds. These winds can be so forceful they eject most of the galaxy's gas reservoir entirely, starving it of future fuel. For the very smallest dark matter halos, this process can be so efficient it leaves them almost entirely dark, with just a sprinkling of ancient stars, perfectly matching our observed ultra-faint dwarfs. But the influence may go even further. The explosive energy doesn't just remove gas, it violently churns the galaxy's gravitational potential. As huge plumes of mass are rocketed outward, the dark matter at the center responds, its orbits becoming randomized and spread out. Over time, this relentless stirring can transform a dense central cusp into a smooth, fluffy core, directly addressing the cusp core mystery. And what of the lonely, quenched dwarfs floating in isolation? The same internal feedback mechanism could explain their silence. A dwarf galaxy, even one far from any giant neighbor, might experience a single, intense burst of early star formation. The resulting supernova could blow out its own gas, self-quenching its growth and leaving it as a red, dead fossil in the void, just like Leo T. This offers the tantalizing promise of a unified solution, where one dominant process, the feedback from stellar life and death, sculpts both the visible and invisible structure of small galaxies. Yet the critical question remains one of scale and timing. Are these simulated winds powerful enough to quench even the most massive, too big to fail halos? those with deep gravitational wells that should cling fiercely to their gas. Can feedback create cores in dwarfs as large as fornax? The latest simulations show promise, but also reveal that the answer is exquisitely sensitive to the precise timing, energy, and distribution of the explosions. It suggests that the final story of our local group's missing satellites may be written not by dark matter alone, nor by stars alone, but in the fragile, explosive, and deeply interconnected relationship between the two. These virtual laboratories are our best window into the past, yet they are not perfect mirrors of reality. The 16th mystery forces us to confront the limits of these simulations. Even the most sophisticated models, like Fire or Illustris TNG, operate within a box, both literally and figuratively. They have a finite resolution, a smallest possible scale they can depict. Imagine a digital photograph. If you zoom in too far, the smooth curves break down into blocky pixels. In a cosmological simulation, this pixel size is crucial. It means we cannot directly model the formation of the very first stars, the legendary population 3 stars. These pioneers were not like the stars of today. They were behemoths, hundreds of times more massive than our Sun, and they burned with a ferocious, pure intensity. Their lives were short, and their deaths were cataclysmic, likely seeding the early universe with its first heavy elements and an unimaginable flood of ultraviolet radiation. We do not know exactly how they formed, how many there were, or the precise details of their explosive feedback. In our simulations, we must use simplified recipes, educated guesses for their effects. If we get that recipe even slightly wrong, the entire chain of events that follows, the quenching of the first small galaxies, could be off by a colossal margin. The uncertainty extends beyond these first stars. Modeling the messy, intertwined physics of ordinary matter is staggeringly complex. How do you accurately simulate the turbulent interplay of radiation blasting from stars, magnetic fields weaving through gas clouds, and cosmic rays, high-energy particles zipping through space? These processes are not side effects, they are central actors. Radiation can heat gas and prevent it from cooling. Magnetic fields can provide pressure support, holding a cloud together or helping it resist collapse. Cosmic rays can deposit energy in distant parts of a galaxy, stirring it from within. Our current simulations incorporate some of these effects, but often in a simplified, approximate way. The true, chaotic dance of these forces is so computationally expensive to model directly that we are forced to make compromises. Could the ultimate solution to the missing satellites problem be hiding in these poorly understood details? It is a profound possibility. Perhaps a more accurate treatment of population 3-star feedback would show they sterilized small halos even more efficiently than we think. Or maybe a better model of cosmic rays reveals a gentle, persistent heating that kept gas in the smallest halos just warm enough to resist collapsing for billions of years. The challenge is that we are using these same simulations to test the solutions. We adjust the physics until the virtual universe looks something like our own, but if the starting physics is incomplete, we might simply be tuning a model to match a reality it does not fully comprehend. This is not a flaw in the science, it is its very nature. Simulations are not crystal balls, they are tools for exploration. They tell us what could happen given a specific set of rules. Their power lies in revealing which physical processes are most important, and their greatest value may be in highlighting the very gaps in our knowledge where the real answers await discovery. Our galaxy's 2 brightest companions may hold a key to the quiet around us. The 17th mystery focuses on the role of the Magellanic Clouds. The large and small Magellanic Clouds are not just random satellites. They are a binary pair, a duo of galaxies locked in their own intimate dance, now falling into the Milky Way's gravitational embrace for the very first time. This fact changes everything. Sophisticated simulations of cosmic structure tell a compelling story. When a massive object like the Large Magellanic Cloud falls into a larger galaxy, it does not come alone. Its own substantial gravity would have dragged along a retinue of smaller dwarf galaxies, a cosmic entourage that has been orbiting it for billions of years. This idea transforms our senses. Could some of the dwarf satellites we already see around the Milky Way, and perhaps many we do not, actually be members of the Magellanic family? They would not be native to the Milky Way's halo at all, but interlopers arriving as a group. This provides an elegant and dramatic solution to one of our deepest puzzles. Remember the great disk of dwarfs, that improbably thin plane of satellites orbiting the Milky Way. If that plane is aligned with the orbital path of the incoming Magellanic Clouds, then its existence is no longer a staggering coincidence. It becomes a fossil of this group infall event. The plane is simply the trail of the Magellanic family, stretched into a disk by the Milky Way's tides. Astronomers are now engaged in a cosmic detective hunt, searching for the fingerprints of this family. They look for dwarfs that share similar velocities, positions, and even chemical histories with the clouds, clues that they originated together in a small group before being captured. Several candidates have emerged, including the Carina and Fornax dwarf galaxies, whose motions suggest they could be part of this extended clan. This reclassification has profound implications for the missing satellites problem itself. If a dozen or more of the dwarfs we see are actually part of the Magellanic group, then the number of true native Milky Way satellites drops even further. The deficit between prediction and observation grows wider and more puzzling. It means the Milky Way's own halo is even emptier than we thought. The hunt for these family members is also a hunt for the truly dark halos. The Magellanic Clouds likely dragged in dozens of their own dark matter subhalos, most of which may have never formed stars. These would be pure dark matter ghosts, orbiting within the Magellanic Stream, completely invisible to our telescopes, but contributing their silent gravity to the local group. So the mystery splits into two questions. First, how many of the dwarfs we see are adopted rather than born of the Milky Way? And second, where are all the dark halos that must have accompanied this grand arrival? The Magellanic Clouds, those brilliant smudges in the southern sky, are no longer mere satellites. They are the harbingers of a lost clan, their brilliant light perhaps obscuring the deeper darkness they brought with them. Andromeda's satellite system presents its own version of our mystery. Our 18th mystery, the Andromeda anomaly, forces us to look beyond our own galactic backyard for answers. The Great Spiral of Andromeda, our closest major galactic neighbor, is a mirror in which we can check our own reflection. If the missing satellites problem were solely a quirk of the Milky Way's history or our limited viewpoint, then Andromeda's entourage should look completely different. It does not, and yet it does in ways that are profoundly revealing. Like the Milky Way, Andromeda is surrounded by a family of dwarf galaxies. Surveys, most notably the Pan-Andromeda Archaeological Survey, or PAS, have meticulously mapped its outskirts. This project provided our first comprehensive, deep look at another giant galaxy's satellite system, giving us that crucial second data point. The similarities are striking. Andromeda also appears to have a vast, rotating plane of satellites, a great disk of dwarfs eerily similar to our own. This suggests that such structures are not a freak accident, but a common feature of galaxy formation, a clue that the processes building these planes are fundamental. Yet the differences are just as telling. Andromeda possesses more bright, star-forming dwarf satellites than the Milky Way. Galaxies like the brilliant Triangulum Galaxy M33 and numerous smaller but active dwarfs contribute to a richer, more vibrant satellite population. So why the disparity? One compelling answer is perspective. We are stuck inside the Milky Way, looking out through its dusty disk. Our view of our own satellite system is obscured and incomplete, like trying to map a city's suburbs while standing in its downtown traffic. Some of our brighter satellites could be hidden behind the thick band of the galactic plane, forever lost in the glare. Andromeda, by contrast, is spread out before us in the night sky, a majestic, near face on spiral. We have a clean, unobstructed view of its entire satellite system. This cleaner view alone could account for some of the difference in counts, but perspective may not be the whole story. The other leading possibility is history. Galaxies grow by consuming smaller ones, and their satellite populations are the leftovers from this cosmic feast. Andromeda is slightly more massive than the Milky Way, and it may have had a more active, or simply different, merger history. It could have recently swallowed a particularly large dwarf galaxy, whose disruption temporarily sparked star formation in other satellites through gravitational shocks, or it might have accreted a whole group of gas-rich dwarfs later in cosmic time. The presence of the star-forming Triangulum Galaxy, itself a substantial system, hints at a more dynamic recent past for the Andromeda system. Studying Andromeda does two vital things. First, it confirms that the missing satellites problem is not just our problem. The theoretical predictions still overshoot the actual counts around Andromeda, just as they do for the Milky Way. This tells us the issue is universal, a fundamental challenge to our models of structure formation. Second, the differences between the two systems act like a control in a scientific experiment. By comparing them, we can isolate which factors are unique to our viewpoint and which are fundamental physics. The great value of the Andromeda anomaly is that it pulls us out of our parochial view. It shows us that while the quiet may be universal, the details of the silence have their own unique story, written in the distinct merger histories of each giant galaxy. The most literal answer to our mystery is also the most elusive. The 19th mystery is the dark galaxy hypothesis. This idea confronts the missing satellites problem with stark simplicity. What if the hundreds of predicted dwarf halos are exactly where the simulations say they should be, orbiting the Milky Way and Andromeda, but they are completely, utterly dark? These would be pure dark matter halos, containing no stars, no glowing gas, not a single photon of light to give them away. They are the ultimate cosmic ghosts, structures built from the universe's dominant matter that failed to ever ignite the ordinary kind. In this view, the problem is not with the theory of cold dark matter, but with our own expectations. The theory predicts dark matter halos, not necessarily galaxies. If conditions were just wrong, if reionization was too effective or gas accretion failed completely, then a vast population of these dark halos could exist all around us, invisible. This would be a resounding triumph for the cold dark matter model, confirming its predictions for small-scale structure, but it would pose a monumental challenge for observational astronomy. How do you find something that emits no light? Astronomers are turning to ingenious, indirect methods, searching not for the halos themselves, but for the subtle shadows they cast upon the visible universe. One promising technique looks for the signature of annihilation. Some theories suggest that when two dark matter particles collide in the dense core of a halo, they could annihilate each other, producing a faint spray of gamma-ray photons. Powerful telescopes like the Fermi Gamma-Ray Space Telescope scan the sky, hunting for unexplained, pinpoint sources of gamma rays that could correspond to dense dark matter clumps. A few tantalizing candidates have emerged, but none have been confirmed as definitive dark galaxies. Another method exploits gravity's lens. According to Einstein's theory, mass bends the fabric of space-time. A compact, dense dark matter halo drifting between us and a distant quasar could act as a gravitational lens, minutely distorting and magnifying the quasar's light in a specific, fleeting way. This effect, called gravitational microlensing, requires painstaking, long-term monitoring of millions of background stars, a monumental task that surveys are now undertaking. Perhaps the most elegant search looks closer to home, at the stellar streams we discussed earlier. These great rivers of stars, the remains of disrupted satellites, should flow smoothly through the halo. But if a dark matter subhalo, a true dark galaxy, were to pass through such a stream, its gravity would tug on the stars, creating a visible kink or gap in the ribbon of light. It would be like seeing the wake of an invisible ship passing through a river of stars. Finding such a perturbation would be indirect but compelling evidence for a dark halo's presence. The hunt for dark galaxies is a frontier of modern astrophysics. It asks us to accept that most of the structure in our universe may be forever hidden from our eyes, detectable only by its silent gravitational influence on the rare, bright matter we can see. Their existence would solve the numerical puzzle of the missing satellites, but it would open a deeper, more philosophical mystery. We would live in a local group where dark matter forms perfect, intricate sculptures in the void, most of which will never know the light of a star. The chemical purity of the ultra-faint dwarfs presents a 19th, and perhaps most pristine, mystery. We have already met these ghostly galaxies, but their true significance lies not just in their dim light, but in the ancient elements that compose them. Stars in galaxies like Segway 1 or Boötes 1 possess metal content, hence hundreds, even thousands, of times lower than our Sun. To an astronomer, metals mean any element heavier than hydrogen and helium, the forged ash of stellar furnaces. This incredible deficiency tells a story of arrested development. These galaxies did not just stop forming stars early. They seem to have experienced only one, or at most a handful, of frantic star-forming bursts before shutting down completely. Their chemical books are not just short, they contain only the first few sentences written in the simplest possible language. This pristine nature makes them our closest link to the universe's infancy, true living fossils. Yet their stunted growth forces a brutal question: what catastrophic event stopped them so abruptly? Was it the global firestorm of reionization, whose pervasive ultraviolet radiation heated their gas and prevented further cooling? Or did they succumb to an internal rebellion, where their own first generation of stars exploded as supernova with such violence that they blew away every last wisp of their gaseous fuel in a single, self-destructive event? There is another, more subtle possibility: external ram pressure stripping. Imagine a dwarf galaxy, even one floating in relative isolation, moving through the thin, diffuse fog of the intergalactic medium. This fog, while incredibly tenuous, exerts a pressure. If the galaxy's own gravitational grip on its gas is weak enough, this constant, gentle breeze could slowly but surely scour its gas away over billions of years, like wind eroding a dune. The ultra-faints, with their shallow gravity wells, would be supremely vulnerable to this patient theft. Their chemical purity is a double-edged clue. It confirms their status as pristine relics, capsules from a time before the universe was widely enriched, but it also deepens the central mystery of satellite evolution, because it shows that the forces which quenched them were not just effective, they were absolute and final. They left these galaxies frozen in their most primitive state, as if time itself stopped for them 13 billion years ago. Their silent orbits a perpetual monument to a universe that moved on without them. The faint afterglow of the first stars may have been accompanied by a more subtle, penetrating rain. Our 20th mystery shifts the focus from explosive blasts to a persistent drizzle of high-energy particles, the impact of cosmic rays. When those first massive stars lived and died, they did not just produce light and heavy elements. Their violent environments, from turbulent stellar winds to supernova shockwaves, acted as natural particle accelerators, launching protons and atomic nuclei at nearly the speed of light. These are cosmic rays, and they flooded the early universe with an invisible, energetic haze. Unlike ultraviolet radiation, which is absorbed by gas, cosmic rays can penetrate deep into molecular clouds. Their influence is complex and dual-edged. On one hand, they deposit energy as they collide with gas particles, providing a gentle but persistent heating that can keep gas from cooling and collapsing to form new stars. This could be a powerful quenching mechanism, especially in the fragile gravitational wells of the smallest halos. A steady drizzle of cosmic rays might have kept their gas just warm enough to remain diffuse, effectively putting star formation on permanent hold. Yet cosmic rays also have a creative side. As they zip through gas, they can ionize molecules, driving a unique chemistry that actually promotes the formation of molecular hydrogen, the primary fuel for the first stars. In this light, cosmic rays could have been a trigger, not a suppressant. This creates a fascinating and messy puzzle. Could the fate of a primordial dwarf halo have been decided by its neighborhood? Imagine a small, pristine dark matter cloud. If it formed near an early, vigorous star-forming dwarf, it might have been bathed in that dwarf's cosmic ray output. Would that external bath of particles have heated its gas, sterilizing it, or would it have catalyzed the chemistry needed to jumpstart its own first generation of stars? The answer likely depends on a delicate balance: the intensity of the cosmic ray flux, the density of the halo's gas, and the precise timing. This pushes our understanding into a frontier where feedback is not a single event, but a layered and interconnected symphony. Supernova blast gas, ultraviolet radiation heats it, and cosmic rays provide a background of persistent energy that can either gently stifle or curiously encourage. It suggests that whether a dark matter halo blossomed into a visible galaxy or remained a dark ghost could have hinged on the chaotic and varied conditions of its local environment over 13 billion years ago. The silence of our local group may be the result of a cosmic lottery, where the smallest halos were the most vulnerable to the capricious weather of the newborn universe. This logical chain of cosmic structure leads to a 21st mystery, a question that pushes hierarchy to its breaking point. If the Milky Way has dwarf satellites, then do those dwarf satellites themselves have even smaller companions? It is the concept of substructure, satellites of satellites, a fractal nesting of dark matter halos within halos. Our cosmological models do not just allow for this, they demand it. In the cold dark matter paradigm, structure builds from the bottom up. The smallest clumps form first and then merge into larger ones. A dwarf galaxy like the Large Magellanic Cloud, which is itself a substantial system, should have captured its own retinue of tiny dark matter clumps during its long history. These would be the cosmic equivalent of moons. Simulations show these minute halos should exist, orbiting within the gravitational sphere of their host dwarf. So, where are they? The hunt for these satellites is a search at the very edge of detection. What would such an object even look like? It would not be a galaxy in any traditional sense. It might be an incredibly faint star cluster, perhaps just a few thousand stars bound together, orbiting not the Milky Way directly, but a dwarf galaxy that itself orbits the Milky Way. Some astronomers speculate that certain ultra-faint dwarfs or peculiar globular clusters could actually be these second-tier satellites. A candidate might be a system like Tucana 5, a faint cluster of stars that shows signs of being gravitationally bound to the small Magellanic Cloud rather than to the Milky Way itself. Finding definitive proof, however, is monstrously difficult. You must first measure the precise motion of the candidate object, then measure the motion of its presumed host dwarf, and finally prove they are truly bound together and not just passing near each other in the vastness of space. For the faintest possible objects, this is a measurement at the limit of our telescopes. The implications are profound. If we confirm such hierarchical clustering all the way down, it would be a stunning validation of the bottom-up model of cosmic structure. It would mean the universe builds in a self-similar pattern, from the largest superclusters down to these minute stellar clumps. But if they are absent, if dwarf galaxies float alone without their own tiny entourages, it would signal a different story. Their absence could point to the devastating efficiency of tidal forces. Within the already crowded and chaotic environment of a dwarf galaxy's orbit around a giant, any smaller companion would be exceptionally vulnerable. The tidal forces from both the host dwarf and the overarching pull of the Milky Way could shred such a fragile system in short order, leaving no trace. Or their absence might simply mark the final frontier of our observational reach. These satellites could be so dark, so star-poor, that they are nothing more than pure dark matter micro-halos with perhaps a single ancient star cluster at their heart, lost in the glare of their host dwarf. Their existence or absence tests the very limits of a fundamental cosmic principle, asking just how far down the chain of gravity the universe's architectural rules truly apply. The race to complete our galactic census is entering its most ambitious phase. Our 22nd mystery is the future of satellite searches, a technological leap that promises to either solve our puzzle or deepen it beyond imagination. The observational frontier is about to be redrawn by a new generation of telescopes, machines designed not just to see farther, but to see the faintest possible whispers of light across the entire sky. Leading this charge is the Vera C. Rubin Observatory, currently under construction in Chile. Its core mission is the Legacy Survey of Space and Time, a 10-year project that will scan the entire southern sky with unprecedented depth and regularity. Its immense digital camera, the size of a small car, will capture the most detailed movie of the universe ever made. For the missing satellites problem, this is a game-changer. The LSST will be sensitive enough to detect ultra-faint dwarf galaxies, so dim they are currently invisible, systems that may contain only a few hundred ancient stars spread across thousands of light years. It is poised to discover not just a few more, but potentially hundreds of new ultra-faint dwarfs around the Milky Way and Andromeda, Simultaneously, the Nancy Grace Roman Space Telescope, set to launch later this decade, will conduct a complementary survey in infrared light. Infrared vision peers through the Milky Way's obscuring dust, revealing satellites that have been hiding behind the thick veil of our own galactic plane. Together, these observatories will deliver the first truly complete map of our local group's satellite population. This flood of new data will force a decisive moment. One possibility is a clean resolution. If these surveys find the predicted swarm of ultra-faints, filling the faint end of the satellite luminosity function with real data points, it would be a monumental victory for the cold, dark matter model. The missing satellites would be found not as bright galaxies, but as the incredibly faint, reionization-suppressed fossils we always suspected. The mystery would essentially be solved, confirming that our theories were right and our telescopes were simply not powerful enough. But the other possibility is far more intriguing. What if, even with this deep, all-sky search, the number of discovered dwarfs still falls dramatically short? What if the luminosity function stubbornly refuses to rise as predicted? That outcome would be a seismic shift. It would mean the deficit is not an illusion of our limited vision, but a fundamental feature of reality. It would force us to accept that a vast population of dark matter halos are truly, completely dark, with not a single star to illuminate them, or that some other, even more effective suppression mechanism wiped the slate clean. Perhaps these future surveys will reveal patterns we cannot yet anticipate, like all newfound dwarfs clustering in bizarre, unexplained alignments, or possessing chemical signatures that defy all models of early enrichment. The Vera C, Rubin and Roman telescopes are not just tools for finding answers, they are engines for generating new, deeper questions. They will transform the missing satellites problem from a theoretical debate into a precise, observational test. We stand on the brink of knowing whether the quiet around us is a trick of the light, or the true, dark nature of our cosmic home. Perhaps the most radical solution to our cosmic silence lies not in finding new matter, but in rewriting the law of gravity itself. This 23rd mystery confronts us with modified Newtonian dynamics, or MOND, a paradigm that dares to ask a startling question. What if the dark matter halos are not missing because they never existed at all? MOND proposes that our understanding of gravity, Newton's and Einstein's magnificent framework, is subtly incomplete. It suggests that on the vast, gentle scales of galactic outskirts, where gravitational accelerations become vanishingly small, the force of gravity strengthens relative to Newtonian predictions. In this view, the flat rotation curves of galaxies, the very observation that sparked the dark matter hypothesis, are not caused by invisible mass. They are simply how gravity naturally behaves in these low acceleration regimes. The implications for our missing satellites are profound. If you eliminate the need for dark matter halos, you also eliminate the expectation of hundreds of dense dark matter subhalos swarming around the Milky Way. The satellite luminosity function, that graph of predicted versus observed dwarfs, changes completely. In a MOND universe, you only expect to see the satellites that actually managed to form from ordinary baryonic matter. The problem, in its traditional form, simply evaporates. Proponents point to intriguing successes. MOND can remarkably well predict the rotation curves of many spiral galaxies from their visible mass alone, without any dark matter parameters. For certain dwarf spheroidal satellites, its calculations of internal dynamics, based solely on their visible stars, sometimes align with observations more neatly than some dark matter models. It presents an elegant, if revolutionary, alternative, cutting the Gordian knot by declaring the unseen matter an illusion of our flawed equations. Yet this radical elegance comes at a tremendous cost. MOND faces monumental challenges when its gaze moves beyond individual galaxies. The first great hurdle is galaxy clusters. When we observe immense clusters like the Bullet cluster, we see a clear separation. The hot, X-ray emitting gas, which is the bulk of the ordinary matter, has been slowed by a drag force during a collision. Meanwhile, the majority of the mass, mapped through gravitational lensing, has sailed right through, clearly separated from the visible stuff. This is interpreted as direct evidence for collisionless dark matter. MOND struggles to explain this separation without invoking some form of unseen particle, which would defeat its core premise. The second, even greater challenge is cosmological. The entire large-scale structure of the universe, the cosmic web of filaments and voids, and the precise patterns in the cosmic microwave background, the afterglow of the Big Bang, are exquisitely fit by models that include cold dark matter and dark energy. Reproducing these pillars of modern cosmology with a modified gravity theory alone has proven incredibly difficult. While relativistic extensions of MOND exist, they often require adding new fields or complexities that begin to resemble the very dark sector they seek to replace. The debate, therefore, remains fiercely alive. It is a tension between elegant simplicity on galactic scales and comprehensive explanatory power across the entire cosmos. MOND forces the astrophysics community to constantly re-examine its assumptions, to ensure that dark matter is not just a convenient fix for every gravitational anomaly. It stands as a powerful reminder that our most fundamental laws are always subject to test, and that the quiet around our galaxies might be whispering not of hidden mass, but of a deeper, undiscovered layer to the force that binds the universe together. This persistent silence around our galaxies carries a weight far greater than a simple accounting error. Our 24th mystery confronts the philosophical implications of this absence. The missing satellites problem is more than a puzzle. It is a potential crisis for the most successful cosmological framework in history, the Lambda CDM model. This model is a thing of profound beauty and predictive power. It has allowed us to trace the universe's evolution from a hot, smooth soup to the vast cosmic web we see today, matching observations of the cosmic microwave background and the large-scale distribution of galaxies with stunning precision. It is the bedrock of modern cosmology, yet here, in our own local group, its predictions fail dramatically. This is not a minor discrepancy, it is a glaring, persistent contradiction between what the theory says should be and what our telescopes actually see. Such a profound mismatch forces a fundamental question upon science. What do you do when your most trusted map of reality no longer matches the territory? One path forward is refinement. Perhaps the core theory is sound, but our understanding of the small-scale physics within it, the so-called sub-grid physics, is crude. We may need to better simulate the chaotic feedback from stars, the subtle effects of magnetic fields, or the persistent drizzle of cosmic rays. This is the work of building a more detailed and realistic virtual universe within the existing rules. Another path is more radical. The contradiction could be a direct hint that dark matter itself possesses unexpected properties. Maybe it is not perfectly cold and collisionless, but slightly warm, or capable of interacting with itself in ways that suppress small-scale structure. This would mean adding a new chapter to the physics of the universe's dominant substance, and then there is the most profound possibility of all, that the crack is not in the details, but in the foundation. Could the force of gravity itself behave differently on the scale of galactic satellites than we have assumed? While challenging, this possibility forces a necessary and humbling re-examination of our most basic assumptions. This tension, however, is not a weakness of science, it is its greatest strength. A beautiful theory that never faces a stubborn fact is just a story. It is the persistent mysteries, the contradictions that refuse to go away, that act as the engines of progress. The missing satellites problem has already driven a revolution in supercomputing, pushing us to create hydrodynamic simulations of breathtaking complexity. It has motivated monumental sky surveys that will map the faintest light in the universe. It has sparked a flowering of creative theories, from warm dark matter to self-interacting dark matter to modified gravity. Each proposed solution, even those that ultimately fail, teaches us something new about the cosmos and the limits of our current knowledge. The quiet around our galaxies, therefore, is not an empty silence. It is a resonant question, one that compels us to look deeper, think harder, and build better tools. It reminds us that our understanding of the cosmos is a living, evolving story, and the most interesting chapters are often written in response to the things we cannot see. Perhaps the ultimate answer is not a single key, but a master keychain. Our final, 25th mystery asks if we can forge a unified theory, one elegant framework that explains the dwarf galaxy deficit, the too big to fail problem, the great planes of satellites, and the quenched isolates all at once. The dream is a cosmic narrative where every strange observation clicks perfectly into place. The current leading candidate is not one mechanism, but a symphony of them, each playing its part at a different time and scale. Imagine the early universe. First, the global fire of reionization sweeps through, sterilizing the very smallest dark matter halos, leaving them either completely dark or seeding them with just a few stars to become our ultra-faint dwarfs. This addresses the faint end of the luminosity function. Then, within the halos that were massive enough to survive this first purge, the internal drama of baryonic feedback takes center stage. Supernova explode, driving galactic winds that not only blow out gas and quench star formation, but also dynamically heat the dark matter, transforming dense cusps into soft cores. This could explain the too big to fail galaxies, those massive halos hosting surprisingly faint stellar populations. For the quenched isolates floating in the void, this same internal feedback might be the culprit, or perhaps the patient, relentless stripping of gas by the thin intergalactic medium over billions of years. And what of the startling planes of satellites? Their story may be one of genealogy, written by Group Infal. The Milky Way and Andromeda may not have accreted their satellites one by one, but in pre-assembled families, like the Magellanic Group, their shared origin fossilized into a rotating disk. This layered story is compelling, and modern hydrodynamic simulations are beginning to show that such a combination can reproduce a local group that looks much more like our own. Yet, for all its promise, this consensus picture still has gaps. Can stellar feedback truly be powerful enough to quench the most massive dwarf halos? Do the chemical signatures of the surviving dwarfs perfectly match the stars in our halo, telling a consistent story of hierarchical buildup? Some researchers argue the date points toward a more radical overhaul. Could the solution lie in the dark matter itself being slightly self-interacting? If dark matter particles can scatter off each other, even rarely, it would transfer heat within halos, naturally creating soft cores and potentially suppressing the formation of the very smallest subhalos from the start. Others look to forces we have only begun to map, like primordial magnetic fields woven into the fabric of the early universe, which could have influenced how gas flowed into the first tiny halos, altering their fates from the very first moment. The search for a unified theory is not about finding a simple answer, but about finding the correct tapestry of cause and effect. While pieces of the puzzle are undeniably falling into place, a complete, consensus picture of our local group's quiet story remains one of the great, unfinished quests of modern astrophysics. It is a reminder that the cosmos reveals its secrets slowly, layer by layer, and the final chapter of this mystery is still being written in the silent motion of stars and the dark spaces between them. The quiet around our galaxies is a story told in 25 interlocking mysteries. We began with a simple, stark deficit: the hundreds of dwarf galaxies our theories predicted but our telescopes could not find. This absence led us deeper into the strange behavior of the dwarfs we do see, galaxies too massive to be so faint, orbiting in improbably thin, spinning planes. We followed clues written in the chemical purity of ancient stars and the smoothed-out hearts of dark matter halos. We considered cosmic culprits from the global fire of reionization to the violent, self-destructive feedback of the first supernova. We explored the possibility of dark galaxies, pure halos of invisible matter, and even questioned the law of gravity itself. From the subtle drizzle of cosmic rays to the grand, incoming retinue of the Magellanic Clouds, each mystery revealed a layer of the cosmic narrative. These missing satellites are far more than just absent objects. They are profound clues, a 25-part cipher that points toward the true nature of dark matter, the violence and complexity of the early universe, and the intricate, lifelong dance between gravity and stellar fire. The solution is not a single revelation, but a tapestry still being woven. This is where you come in. The next chapters of this cosmic detective story will not be written in theory alone, but in the flood of new data from the Vera Sea. Rubin Observatory and the Nancy Grace Roman Space Telescope. Their deep, systematic surveys of the sky will complete our census, finding the faintest dwarfs or confirming the depth of the darkness. Stay curious, watch the headlines. The solution to what shapes our galactic neighborhood, and by extension, the universe itself, is being written now, in the silent light collected by these magnificent machines, in the data of the night sky waiting to be read.